Thank you for tuning in. I am VM Krishnarao Kotteda. I present our work on Trilinos solver scalability on a MFiX-Trilinos framework applied to fluidized bed simulations. This is the outline of my talk. First, I give a brief introduction to multi-phase flows and brief introduction to the one of the solver to simulate gas-solid flows, and I'll describe the shortcomings in that open source software and how we address those shortcomings and how we validated the new solver and analyze the performance of the new solver on various computing architectures. The multi-phase flows involve matter with different phases. The multi-phase flows involves matter with different chemical substance but with the same phase. The multi-phase flows are important in many industrial processes such as coal-fired furnaces, fluidized bed reactors, liquid sprays, scrubbers, dryers, paper manufacturing, food manufacturing, and medical applications. MFiX is one of the multi-phase software to simulate gas-solid flow. It is written in Fortran. It is developed by National Energy Technology Laboratory. It is widely used by fossil fuel reactor communities to simulate gas-solid flow and design a reactor. It provides three suites of models that treat the carrier phase and disperse phase differently. The three models are two-fluid model, discrete element model, and particle in cell model. The two-fluid model is based on the Alerian approach. The DEM and PIC models are based on Alerian-Lagrangian approach. The solution time and the model uncertainty of these models in the MFiX are shown here. So the gas-solid flows are addressed by solving coupled continuity, momentum conservation, energy equation, and parameterizing many effects. So here I'm showing the governing equations for some of the flows, and we discretize these equations with a finite volume method, such as a simple algorithm, and get the linear system of equations. We usually use iterative solvers to solve the linear system of equations. This is the model development and validation activities at National Energy Technology Laboratory. This is the small scale CF fluidized bed, and this is the small scale bubbling bed with image analysis. This is the granular flow, and this is the particle separation and flow control. This is the reacting bed. So MFiX does not have advanced linear solvers, and it is not portable on various computing architectures. So we can leverage these features from an object-oriented framework. So one of the object-oriented framework is Trilinos. It is developed by Sandia National Laboratories. So our goal is to develop, validate, and implement advanced linear solvers to replace MFiX existing linear solvers. This goal is achieved by integrating Trilinos with MFiX. Demonstrates scalability of the integrated solver on various high-performance computing architectures, and the expected results will be reduction of computational time. So that will greatly speed up the design of the reactor. Our objectives are create a framework to integrate MFiX with Trilinos, validate MFiX suite of problems on HPC systems, and evaluate the performance. What is the Trilinos, or what is the object-oriented framework used in this present study? So this object-oriented framework is developed at Sandia National Laboratory. This allows us to solve big complex science and engineering problems. This library is more like a Lego bricks than a MATLAB. It has different packages. It provides state-of-the-art preconditioners and linear solver libraries. It demonstrated scalability on various HPC systems. It has plans for continued maintenance. Uh, it supports the existing hybrid computing architectures. It allows us to get the portability by using the Cocos library in Trilinos. Earlier, I mentioned that Trilinos has 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 more than 60 packages. So some of the packages are linear solvers, services, tools, direct linear solvers, iterative linear solvers, preconditioners, nonlinear solvers, eigen solvers, optimization analysis, mesh and load balancing, discretizations, and performance portability. The performance portability is achieved by using the Cocos library in Trilinos framework. The Trilinos has three generation of packages. The first generation packages are essential packages. The second generation and third generation packages allows us to solve the problem that contains more than 2 billion unknowns. Uh, the third generation packages are portable, and so we can get the performance on hybrid computing architectures by using the third generation packages. So this is the interface that we use to integrate MFiX and Trilinos. This is the flowchart. Uh, this is the flowchart of MFiX. So this LEQ is the keyword to set the linear solver in MFiX. If the keyword is less than 5, then it uses the existing solvers in MFiX. If it is set to equal to 6 or greater than 6, then it uses the solvers in Trilinos. The interface that we developed contains MFiX, Fortran, C, and C++ wrapper. Most of the action is taking place in CPP wrapper. In the CPP wrapper, we solve the linear system of equations with iterative solvers in Trilinos and pass the solution to the MFiX wrapper or MFiX via C and Fortran wrappers. Next, I'll show the list of operations that we are currently doing in the C++ wrapper. First, we create a map, and we use that map to create a sparse row matrix and the left hand side and right hand side vector. So the non-zero entries in the sparse matrix is filled with insert global method. The right hand side vector is formed with sum into global values method in Tripetra. In this step, we are forming the linear problem, and here we set the preconditioner, and in this step we set the iterative solver, and at the end we solve the linear system with the iterative solver, and we return the solution to MFiX via C and Fortran wrappers. So we have the integrated solver, and we have to verify the solver on various gas solid flow problems. First, we considered 2D fluidized bed. This is a bubbling bed. The properties of particles and the fluidizing agent is shown here. So here we compared the TFM model in MFiX-Trilinos with the same model in MFiX. The solution with the TFM model in MFiX-Trilinos is same as the same as the solution with the same method in MFiX. So here we considered a flow in a 3D fluidized bed in 3 dimensions. So here again we use a two fluid model. The solution with the two fluid model in MFiX-Trilinos is compared with the um, same method in MFiX. So the solution with the MFiX-Trilinos and MFiX are same. Next, we validated the DEM and PAC models in the integrated solver. Here we compare the DEM model. So here we compare the solution with the DEM model in MFiX-Trilinos with the same model in MFiX. And here we compare the a solution with PIC model in MFiX-Trilinos with the same method in MFiX. So the solution with the integrated solver is same as the solution with the original solver. So next we perform the performance analysis on various supercomputers. First we carried out this analysis on Stanford. Stanford is a Texas Advanced Computing Center. So here we are showing the wall time for different problem size and different processing elements. As expected, the solver time decreases with processing elements while it increases with the problem size. So next we carried out the performance analysis on Stampede, Comet and Bridges. So here on the y-axis we are showing the solver time in MFiX to the solver time in Trilinos. On the x-axis we are showing the number of processing elements or number of processors. So here we can see that for two different problem sizes, the solvers in MFiX-Trilinos are more than 1.5 times faster than the solvers in MFiX. The summary: the advanced linear solvers in Trilinos are integrated with MFiX via MFiX Fortran C and C++ wrappers. The framework has been validated on various fluidized bed problems. The performance of the validated integrated solver is studied on various supercomputers for various fluidized bed sizes. As expected, the solver time decreases with the processing element while it increases with the problem size. So I would like to thank UTEP, Department of Energy, EFRL and Indian National Labs. Special thanks to Exceed and the Texas Advanced Computing Center for allowing us to carry out the performance analysis. Thank you for your attention.